Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 15, 2025, just yesterday. The big contribution is a new large-scale, multi-domain, multi-modal dataset that finally gives 4D world modeling the diverse, richly annotated data it has been missing, and fine-tuning on it delivers clear gains across 4D reconstruction and camera-controlled video generation. The paper is titled OmniWorld, a multi-domain and multimodal dataset for 4D world modeling, and the implications for model training are quite significant. In short, the dataset unifies synthetic and curated real sources with depth, poses, flow, masks, and captions, and it establishes a tough benchmark that exposes current limitations. Also, the authors shared a GitHub repo. You'll find a detailed README with dataset overview and news, download instructions via Hugging Face, a scripts folder including Visualize PCD to turn scenes into point clouds, example data structure, and licensing notes. The repo highlights the OmniWorld-Game subset and benchmark details. Alright, Figure 1 introduces the dataset scope and signals why it matters. It combines many domains and modalities, so models can learn both 3D structure and motion over time. The collage highlights depth maps, camera poses, optical flow, masks, and long text captions, which together provide supervision across geometry and dynamics. The banner also emphasizes scale with hundreds of millions of frames, so training can cover diverse scenes. The takeaway is comprehensive data breadth for 4D world modeling. So Table 1 makes the case that OmniWorld-Game offers broader modalities and larger scale than prior synthetic datasets, which matters because world models need matched geometry and motion signals. The table lists scene type, motion, resolution, and frame count, then marks whether depth, camera poses, text, optical flow, and foreground masks exist. Most prior sets miss at least one key modality, while OmniWorld-Game covers them all. The takeaway is comprehensive supervision at significant volume. Alright, Figure 2 shows how the dataset turns raw footage into rich, synchronized labels, so models get geometry and motion that actually line up. The pipeline starts with 4 domains, then filters videos for quality and outputs depth, camera poses, optical flow, masks, and long captions. Depth comes from renderer depth or learned stereo, which means distance per pixel is known. Camera poses use coarse estimation, then dense tracking with bundle adjustment, producing a fused point cloud. So Table 5 reports how well current video generators follow camera commands while keeping footage realistic. Camera control accuracy uses translation error, rotation error, and a camera motion consistency score, which together capture how closely the generated path matches the instructed path. Cam control achieves the best control and the lowest free-shave video distance, so it balances fidelity and obedience better than the others. A C3D shows basic control but much higher distance, indicating weaker visual quality under text prompts. Okay, 2 takeaways stand out. The dataset finally supplies broad, synchronized signals for geometry and motion at meaningful scale, and fine-tuning on it measurably boosts reconstruction and camera-controlled video generation, especially on long, dynamic sequences. The broader implication is clearer pathways to general 4D world models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.